This R2R resistor ladder DAC is able to convert a digital input of 9 volts into 256 different analog values. To help explain how the R2R DAC works easier, I have simplified my 8-bit R2R DAC into 4 bits. If you were to want to calculate the resistance at the output, it would seem difficult in the circuit, but it's actually the opposite. We would do this through Thevenin's equivalent circuits. Thevenin's equivalent circuits tell us that as long as the circuit only contains linear elements, like resistors, we can break a circuit anywhere we want. In that simplified area, we need all the resistors to have the Thevenin resistance. To find out that, you simply use the parallel resistance formula, which you can see down here. This formula is for these two resistors for now. These two resistors both go into here, 2R, 2R, and when you do the math, it comes out to 5.1 kilo ohms, being the Thevenin resistance for this point. If you flip it over, you can convert the circuit into this. And now we have two 5.1 kilo ohm resistors, which you can put together to equal 2R, and then it's 2R in parallel with 2R, and that equals another 5.1 kilo ohm resistor through this. And you turn to this. And we can keep doing this again and again, and it keeps going until we have 1R, or 5.1 kilo ohms, being the resistance at the output. To calculate the voltage at the output, we can use both superposition theorem and Thevenin's equivalent circuits again. To do this, we need to use superposition theorem, and to do that, you must short all independent voltage sources except for the one that you were using. So imagine we have the voltage going into bit 0, which is going to be 9 volts, but we're going to keep it as voltage for bit 0 for now. And it's going through two equivalent resistors into ground, as we are assuming that it's cut off at this point. And we want to find the voltage here, and since these two resistors are equal, we know that the voltage will be half. And then we have this 5.1 kilo ohm resistor from Thevenin's equivalent circuits, and these two combine into 2R, and then we have a 2R and a 2R in parallel, so the voltage will half again. And then we have another RR, 2R, the voltage will half again. And the same thing, we'll do that one more time. And now we have, at the output, for bit 0, it will give 9 volts over 16. But if this were in our 8-bit circuit, bit 0 would give 9 volts over 256. And to find the voltage at the output, like the total voltage at the output for the circuit, we do this for every single bit. So bit 1 will be, in this 4-bit simulation circuit, will be VB1 over 8, as it has one less halving it has to do. The breadboard prototype demonstrates the principle as shown on paper. As you can see, as the voltage is slowly increased through more and more switches being flipped on the switch bank, it exponentially gets larger and larger, as shown through the superposition theorem. This will continue until the maximum voltage has been reached. This is the device for the R2R resistor ladder DAC. As you can see, with all the switches off, the voltage is 0 at the output. And as we slowly turn on bit 0, nothing changes up here because the change is so small, it's unnoticeable by the voltmeter. But as we slowly keep increasing, we get 0.2. And we keep increasing until we reach the maximum voltage, which is 8 volts currently, due to the battery being weaker.